Good afternoon, students. Am I audible?
Yes, sir.
Okay. So, we'll get started. Can someone tell me what was the last topic we were discussing?
Inductance.
We started
about the significance of inductance.
Yes. Yes. So I explained the significance of inductance, right? Then I told you I'll explain about self-inductance, mutual inductance of solenoid. Right. We'll get started. So before we get started with self-inductance, let's just recollect what does inductance mean. So what does inductance mean here? Anybody? So inductance is defined as the ratio of the amount of flux divided by current. I told you, right? The mathematical value is N phi divided by I. And it is also the property of an inductor to oppose the rate of change of current. So inductor is a device which will oppose the rate of change of current. So it does not allow the current to change with respect to time. And there is a reason why an inductor does not allow AC to pass through it. Okay. Then we'll go to the concept of self-inductance of a solenoid. Right. So, if I have a solenoid like this, listen guys. If I have a solenoid of length L and which is connected to a power source with the help of a switch like this. Okay. So let's say its voltage is V and the switch is open. Okay. So when the switch is open, obviously the current is going to be zero, due to which magnetic field is zero, due to which flux will be zero, as a result of which the induced EMF is obviously going to be a zero, right? Whereas when the switch is closed, what is going to happen? I will increase, which is going to be a non-zero value. B will increase, flux will increase, and the induced EMF is not going to be zero anymore. Right? So in this kind of a scenario, what will happen is there will be an EMF which will get induced across the ends of the solenoid, which we generally call it as the back EMF. Okay. It is called as back EMF or self-induced EMF. And the reason why we call this as back EMF is very simple, because the EMF that is getting induced will try to oppose the cause according to Lenz's law. That is the reason why we call it as a back EMF. Okay. Now, the question is, what is the value of inductance of this solenoid? So what we will do, let's take the length as small l instead of taking it as capital L, because small l, capital L is used for inductance, right? So what is the basic formula for inductance? L is equal to N into phi B divided by I. Now we need to ask certain questions. So here, who is producing the flux? The flux is produced by the solenoid itself. So we can say L will be equal to N into, what is the value of phi B? The value of phi B due to a solenoid is mu naught into Ni divided by the current that is getting, the current that is flowing through itself. So I and I will get cancelled in this case. So L will be equal to mu naught into capital N into small n. But we know that small n is nothing but, 1 minute, I made a mistake. So phi b, that is mu naught Ni, that is B into A, the area of the conductor. So here area will also lie, right? So this will be equal to mu naught into, can I write capital N as small n into L? So if I take this and substitute it here, I'll get small n into L into N into A, which is called as L. So L will be equal to mu naught N square L into A. So this is going to be the value of the self-inductance of this solenoid. Okay, so this is one of the formulae. Or we can write L is equal to mu naught into capital N, capital N is left as it is. Small n can be written as capital N divided by L into A. This is equal to mu naught capital N square A divided by L. So you can either use this formula, first formula, or the second formula to solve the problems whenever you are asked to calculate the self-inductance of a solenoid. Okay. Now you guys can make a note of it.
So can you scroll a little bit up?
Sure.
Oh, okay, thank you.
Sir,
Tell me.
sir, could you explain like what each symbol stands for once?
What?
The formula, final formula, what does each unit stand for, sir? NLA.
Sure, sure.
Yes,
So somebody asked me for the page. Is it over?
Yes, sir. Thank you.
Okay. So each value, what does it stand for? L, the overall unit is Henry. Right. So mu naught stands for what? Permeability of free space.
Permeability of free space.
So the unit of this is Tesla meter square per ampere. Capital N, no units because it's a number. Area stands for meter square. L stands for meter. So Tesla meter square per ampere into meter square divided by meter. This will get cancelled. It will be Tesla meter cube per ampere, which is collectively called as Henry. Okay.
So here L is length of the coil, N is the number of loops, sir.
Okay, that is what your doubt is. L is
Length
small
of
and
the
the length of the coil. That is a solenoid here. Capital N stands for number of turns, and small n stands for the number of turns per unit length.
Sir, can you scroll up a bit?
Sure.
base area, right, sir?
Sorry?
Base area, right, sir?
AC area, yes.
Sir, can I explain why did you multiply capital and like number of turns per unit length and number of turns, sir, in the first step?
Because it is there no capital N into small n. Mu naught Ni is the magnetic field due to the solenoid. Capital N is the number of turns of the solenoid. Right. So the flux produced due to it will be N into mu naught into N into I. That is the reason I multiplied. Got it?
Yes, sir.
Okay. So moving on to the next one. Now we will see mutual inductance of two coaxial solenoids. This one. So let us say we have two coaxial solenoids like this, where capital N1 stands for the number of turns of the coil that is there inside, and N2 stands for the number of turns for the coil that is there outside, and L stands for the length of it. Okay. Now, let R1 be the radius of the inner coil and R2 be the radius of the outer coil. Now, our job is to find what is the mutual inductance of the two coaxial solenoid. The meaning of mutual inductance is, so before we see what is mutual inductance, let's first try to understand what is the process that is going to happen. Now, if I consider a coil like this, let's say there is a coil that is connected across a battery, and it is connected with the help of a switch. Okay, let's say there is something like this, where this is the, okay, forget about length also, where this is one of the coils, and there is another coil which is placed near it, which is connected to a galvanometer. So this is the primary coil, and this is called as the secondary coil. So let me be more clear. So primary coil is the one which is connected to the battery, and the secondary coil is the one which is connected to the galvanometer. Okay. It will not have any current of its own. It is because of the change in flux happening in one coil, you can observe that there is an EMF getting induced in other coil. Okay. So I hope you understood what is a primary coil and what is a secondary coil. Right. Now the next question is, when you close the switch, what is going to happen? There will be an increase in flux that is taking place. And when there is an increase in flux, the same flux will get linked with the second coil as well. Right. So the flux generated by the first coil will get linked to the flux in the, will get linked to the second coil, due to which what will happen? There will be a change of flux taking place in the second coil, as a result of which you will be able to observe that this second coil will show a small deflection in the galvanometer. Clear, guys? Right. And this kind of a process is what is called as mutual induction. Okay. Induction is a process. So what is it? The process of generating EMF in the neighboring coil due to the change of flux produced by the primary coil is what we call it as mutual induction. This you would have learned in your 10th standard as well. Right. Now, can I say, if I take this as the first coil, this as the second coil, can I say that the flux linked with the second coil is directly proportional to the current that is passing through the first coil? It is because of the current to the first coil only magnetic field is getting generated. Due to that magnetic field only flux is generated, and due to that flux only the flux is getting linked to the second coil. So the flux that is getting linked to the second coil is actually generated due to the current in the first coil, right? So if you remove the proportionality symbol, we can say N2 into phi2 is equal to M21 into I1. What is the M21? M21 stands for the M21 stands for the mutual inductance of the second coil with respect to one. Then this M21 can be called as N2 phi 2 divided by I1. Okay, so M21 will be equal to N2 phi 2 divided by I1. And this is called as the mutual inductance of the second coil with respect to first coil. Okay. In a similar way, you guys tell me what can be done. So for mutual inductance to, or for mutual induction to take place, we know that two coils are necessary, right? So out of those two coils, what you can do, you can swap whichever you want as the primary coil to the secondary coil. Suppose I call the first coil as primary and second as secondary. Now what we can do is we can take the battery from the first coil and connect it to the second coil, and galvanometer from the second coil and connect it to the first coil. As a result of which, now second coil will become primary and the first coil will become secondary. We can even think of this kind of a scenario, where this is still the first coil, and this will be the second coil, right? Now I can say that this coil is secondary because that is the one which is connected to the galvanometer, and I can call this coil as the primary, right? When I do this, what I can say is, can I say that the flux linked with the first coil is directly proportional to the current flowing in the second coil? So N1 phi 1, I'm saying it is directly proportional to I2. Then N1 into phi 1 will be equal to M12 into I2, which implies M12 is equal to N1 phi 1 divided by I2. Then this M12 can be called as the mutual inductance of first coil with respect to second. I can say this.
Sir?
Tell me.
Sir, in this diagram, the electric flux in the the magnetic flux in the secondary coil, you took it as 0, right, sir? Initially,
Yeah,
sir.
because I put the switch open. When you close it?
No, sir, in the secondary coil, I'm saying, sir. Coil which has a galvanometer.
Yeah, see, current diagram basically 0, but as soon as you close the switch, then what will happen? Then flux will get linked.
Okay.
Sir, can you scroll up?
Sure.
Yes, sir. Thank you.
Sir?
Tell me.
Sir, after the flux, that is after the switch is closed, flux will be generated, no, sir? Will the flux be equal in both the coils or will it differ, sir?
It will be different only because in this kind of an arrangement, there will be some leakage taking place here. Okay. So that's the reason why whenever you have two coils, it is very important to choose the orientation in which you place the coil so that the flux leakage is reduced. And if you see, I wanted to explain the concept of mutual induction. That is why I drew this kind of a diagram. But if you observe the diagram that is given here, what have they taken? They have taken two solenoids which are coaxial. So the reason why they took it as coaxial is because the flux generated by the primary coil will get completely linked to the secondary coil in both the scenarios. So what do I mean by both the scenarios? Since you have two coils, how many combinations are possible? You can take the first coil as primary and the second coil as secondary, or you can take the first coil as secondary and the second coil as primary. Right? When you do that, in both the scenarios, since these two solenoids are connected coaxially, it is ensured that the complete flux produced by the first coil will get linked with the second coil. Here, what do I mean by first coil is the flux generated by the primary coil will get completely linked with the secondary coil. That is what I meant. Okay.
Yes, sir.
Now I'm moving on to the derivation part. Let me take this diagram and copy it. Now listen. So if I take S1 as primary and S2 as secondary, if I take S1 as primary and S2 as secondary, then can I say that the flux linked with the secondary coil N2 is directly proportional to the current that is generated by the first coil. So N2 is directly proportional to I1, and N2 into phi2 will be equal to M21 into I1. Then what is going to be the value of M21, guys? It is obviously N2 phi2 divided by I1. Now our job is to write phi2 in terms of B and A and then get the exact value of M21. So M21 will be equal to N2 into, what is the value of phi2? It is a magnetic field into area into cos theta, the whole divided by I1. So look at the way I'm going to write the values. So what is the value of B1, phi2? Phi2 is nothing but the flux produced due to the second coil. Sorry, magnetic field generated due to the second coil, because I'm sorry. So N2 into, what is the value of B? B will be nothing but B1. Why should I write B1 here? It is very simple, because the first coil is the one which is connected to the battery. So the first one is producing the magnetic field. Okay. Into what is the amount of flux that is present through the second coil? This is where we need to be careful, guys. Observe. So we know that the magnetic field due to a solenoid is completely linked within itself of value mu naught into N into I. So it is getting completely linked with the coil itself. As a result of which, what we can conclude is, whatever is the flux that is present through the first coil will be the exact value of flux that is present through the second coil as well. Right? So here, though it is written as phi2, whatever is the flux that is present within the first coil will be the same flux through the second coil also. Because if you recollect the concept from the previous chapter, what did I say? Magnetic field due to a solenoid is completely linked within itself. If you consider it to be a long solenoid. What do you mean by long solenoid? Its length is more compared to the radius. The same thing is happening here. And theta is obviously going to be 0 degrees. So it will be N2 into B1 into A1, the whole divided by I1. Now see, this will be N2 into, what is the value of B1? B1 is mu naught into small n into I1 into A1, the whole divided by I1. I1 and I1 will get cancelled. It will be mu naught into small n2. Okay, I'll write it as N1 here. Small n2 into the length of the solenoid into N1 into A1, the whole divided. Okay, that's it. So this will be how much? It will be mu naught N1 into L into A1.
Sir, can you explain the last before step, sir?
This one.
No, sir. This one. After this step, sir.
Okay. So mu naught into N1 into I1. Okay. So capital N2, I wrote it as small n2 into L. Sorry. Small n2 into L. Okay. So that is why n2 into L. N1 is as it is. I1 and I1 will get cancelled and A1 is left out. So it will be mu naught N1 into L into A. That's what I wrote it. Is it clear?
Yes, sir.
Now, unlike the self-inductance, in mutual inductance, we have to calculate both the values. Both the values in the sense, we need to find M21 and M12 also. So what is M12, guys?
Sir, actually, I have a doubt here, sir.
Tell.
Sir, M21 is the inductance of first coil with respect. Sorry, sir, with the inductance of second coil with respect to first coil, no, sir.
Correct.
Sir, then A2 should come, no, sir, because I'm calculating for
That's
the
what
second coil. Sir.
That's what I told. A2 will not come because the magnetic field itself is present within whom? The first coil is connected to the battery. It is the one which is connected to the battery. So when it is connected to the battery, there will be a magnetic field inside the solenoid. So if you revisit the concept of solenoid and recollect, the magnetic field is present only within it and its value is mu naught into N into I. Outside it is 0, here also it is 0. This concept we already discussed in 4th chapter. When that is the case, then the total flux that is getting generated is within whom? It's within the first coil itself. Though you have a bigger coil, what is happening? Whatever is a bigger coil, the total flux is restricted within the first coil itself. See, for example, I have a question like this. Let's say there is a point charge Q and you have a sphere of radius R1. So if I say the flux through this is phi1 and the same charge Q is there and its radius is increased to R2. Now what is going to be the flux in this case? Is it going to increase or decrease?
Increase, sir.
It will still be the same.
Sir, but
Because
flux
what
is...
I'm no flux
No,
is
sir,
equal
flux
to
is...
Q divided by epsilon naught.
Sir, but magnetic flux is BA cos
I'm
theta,
not. I'm
sir.
talking. No, that I know. I'm not talking about that. I'm asking you in terms of Q null charge. I'm asking about electric flux. So flux is equal to Q divided by epsilon naught. Now, if the charge enclosed by the Gaussian surface is same, then it is going to be the same irrespective of the area that we are going to consider. Now, see, what I'm doing is, let's say there is an area through which the flux is calculated. And if I call this flux as phi1, okay, I'll explain it in a different way. Listen. So when you see the solenoid from this side, when you see the solenoid from this side, what will happen? They will appear like small circular loops. So if I call this as S1 and this as S2, so then the magnetic field is present only within S1. Then how much is the flux linked with it? If I call this flux as phi, whether you consider another solenoid around it of radius R or R1 or R2, what is going to be the total flux that is going to get linked with the bigger coil? It is only the region. So it is only through the region where it is shaded. You're able to understand? Because magnetic field is present only in that region. You should not go and apply the formula B into A, where A you will take it as the area of the bigger coil. What does the definition of flux tell? The amount of magnetic field that is passing through a given area. So the magnetic field itself is present only in this part of the area. Right? Then how can you multiply A2?
Sir, so we should take. Sir, so we should
that
take
is
the
reason
area.
why. That is, yes, that's right. So that is the reason why I took it as A1. This is an important step. Okay, this is the place where many people make mistake. See, the same question comes as an objective question, right? Like how they have planned this year. It will definitely confuse you. So I suggest everyone to make a clear note of what I explained. Because everything will look unique. B1, A1, B1, A2, B2, A1, B2, A2. 4 options. They look alike. It will confuse you. Most probably people will take B2, A2. But you should have a clear vision of what exactly is happening inside. Okay. So I hope everyone is clear with what I explained now.
Yes, sir.
Okay. Now you guys tell me how to do M12. M12 will be equal to N151 divided by I2. Right. So what is N151? Now what is happening? The second coil is connected to the battery and the first coil is connected to whom? Nothing. Galvanometer. Right. So N1 is N1 only. Here flux produced the first coil. It is happening due to the magnetic field of the second coil into the area of the first coil into cos 0 degrees, the whole divided by I2. Why I wrote B2A1 here is because, observe, there is S1, there is S2. Okay. When there is S1 and S2, the magnetic field due to the current in the coil S2 is completely within this bigger circle. But what is the amount of flux that we need? The flux is present only in this region. So understood, guys? This magnetic field is B2. This area is A1. So we are concerned about the flux through the first coil. The flux through the first coil is nothing but the magnitude of the magnetic field of the second multiplied with the area of the first coil. So B2 into A1 into cos 0 degrees. Am I clear?
Sir, I can't understand how it is A1. It should be A2, right?
Adama, Trip, you should be clear about it. You guys need to understand this point. Okay, let's say this is the area A1. Okay. There is a magnetic field present outside. Let me call this as B. If I ask you what is the flux through this portion, what will you say? You will say magnitude of the field that is present here into A1. Why? So magnitude of the field present is constant. It is B. Correct?
Yes.
Fortunately, here constant field. Then why are you not concerned about these field lines?
They are not passing through the given area, sir.
Through the area where you are interested to calculate. In a similar way, B2 is present everywhere within the circumference S2, within the area of S2. But what are we concerned about? We are concerned only about the flux that is passing through the first coil. Right? Means how much this region is enclosing, how much of the magnetic field lines is this region enclosing is what our interest is. Then what are we supposed to write? We are supposed to, in a simple, like how you ignore the outside field lines of that area, you are supposed to ignore these field lines also.
Yes, sir. Understood, sir.
Got it? Yes. So that is the reason why it is B2 into A1 into cos 0 degrees. This also you need to be careful, guys. So there is an important point that you need to note. In the case of mutual inductance, okay, whether you are calculating M21 or M12, the common point is the area that you are taking into consideration is always the area of the smaller coil. Okay, so the area that we take into consideration is always the area of the smaller coil. Please make a clear note of it. Then I can say M12 is equal to N1 into what is the value of B2? B2 will be mu naught into N2 into I2 into A1, the whole divided by I2. I2 and I2 will get cancelled. Now what will happen? It will be mu naught into capital N1 is nothing but N1 into small l into N2 into A1. So what will be the answer, guys? Mu naught N1 N2 L into A1. Now, refer your notes. Tell me what is the relation of magnitude between M12 and M21.
Zero, sir.
They're equal.
Sir, but I have a doubt, sir.
Tell me.
Sir, while calculating for M21, sir, so S1 is the primary, no, sir. So it will be big, no, sir. The coil will have a large area than the secondary coil, no, sir. In the previous diagram, sir.
No, they don't have same area. I mean, what do you mean by S2? You are saying S2 will have greater area than S1.
No, sir. While calculating for M21, the bigger coil is the primary and the coil which is inside is secondary, no, sir. Then A1 will be greater than A2, no, sir.
No need, no. Why will A1 be greater than A2? Because I'm not taking A1 and A2 according to phi1 and phi2, no. I'm looking at the logic. I'm trying to see how much is the magnetic field present and the flux that is getting associated. When we calculated M21, you are interested to calculate. 1 minute, wait, 1 minute, wait. One minute, wait. Guys, I'm really sorry. I actually swapped and wrote everything. See, N2 into phi2 is nothing. Phi2. No. I'm correct. I'm sorry. I'm right only. So N2 into phi2. I'm calculating how much is the flux that is getting linked with the second coil, which is generated due to the current in the first coil. Look at the denominator, I1. Now, what is your question? Tell me clearly again. I didn't understand.
Yes, sir. So A1 is the area of the primary coil, no, sir. That is S1, right?
That's right. Yeah, smaller coil, yes.
And in the second one, oh, sir, you took S1 as primary. Okay, sir. I got confused. I took S2 as primary, sir.
No. S1 is primary. S1 is primary. Because you have to look at the denominator. The denominator, see guys, there are certain tips to be remembered here. The flux that is there in the numerator is generally for the secondary coil. And the current that is there in the downward one is from the primary coil. Whether you take M12 or M21, that is a thumb rule, okay? This point is purely based on observation. Nobody will tell you this. So numerator, when you're writing the formula for M21, corresponds to the flux of the secondary coil. And the current in the denominator refers to the primary coil. So if you have made a clear note of it, then if you observe self-inductance, no. So what will happen in self-inductance is the numerator and denominator both belong to the same coil. That is the reason why it is called as self-inductance.
Can you repeat it again, sir?
So for self-inductance, the numerator, the flux that is getting linked and the current that is flowing through are through the same coil. So that is why we call it as self-induction. It is called self-induced EMF. Whereas in this case, what will happen is the flux will be in one coil, the current will be in another coil. That is why we call it as mutual induction. Similarly, to make it more clear, when you take M12 is N151. So N151 now is the secondary coil and I2 is from the primary coil. So looking at it, you can say that the power source is connected to the second coil, S2. And the flux is changing within the first coil, that is S1. Okay. So I'm moving on to the last topic. See, last class I told you that generator is not there, but when I checked the syllabus again, what they did is they gave generator also in the 7th chapter. See, I thought it is we have only till mutual induction, but in this chapter also there is nothing that is deleted. Did I discuss about eddy current?
No, sir.
No, right? Okay, then we will discuss about eddy current and then we'll go to the concept of AC generator, which is the last topic. So AC generator we'll discuss tomorrow and then link it to the next chapter. So it is given here. So don't look at the syllabus and get confused. AC generator actually belongs to the 6th chapter. Okay, we'll get started.
Sir,
So write down the heading. Tell me.
Sir, if two coils have same area, can they be coaxial, sir?
No, they cannot be coaxial. They will overlap on each other. That's not. Then the EMF will not get induced without physical contact. If you need something to get generated without physical contact, especially when they are coaxial, then you need to ensure that the areas are different. See, coaxial generally means like this. Co generally, the naming structure means same. Axial means axis. So if both the coils are sharing the same axis, then we call them as coaxial.
Okay, sir.
Okay, now write down the heading as eddy current. Okay. So the topic that we are going to see now is this. This is the one. Okay. So just give me a second. Listen, guys. So now we will see the concept of eddy current. Okay. With the help of this activity, we'll try to understand what it exactly means. Now, they have
another demonstration of eddy.
A magnet in his hand, right? He has a magnet in his hand where one is going to be the North Pole and the other is going to be the South Pole, obviously. Now, what will happen when you try to pass a ferromagnetic substance into it? What will happen when you try to pass a ferromagnetic substance into it?
It will get attracted, sir.
It will get attracted, right? Whereas when you pass a paramagnetic or a diamagnetic substance, what do you think will
Later attract or repel in a peak manner.
But they have feeble attraction and repulsion, right? They are not going to show a very great extent of attraction or repulsion, right? So for that purpose, what they will do is, he will take an aluminum sheet and try to swing it through this magnetic field. Then see what will happen.
Currents and the resulting magnetic braking that will occur on a pendulum. So what I have here are two magnets. Okay, so this is like the North Pole here of this magnet and the South Pole here of this magnet. So there's a fairly uniform field in between here, and these are actually fairly strong magnets. So if I actually put a piece of steel in here, if this were a piece of steel, it would stick and I probably wouldn't be strong enough to pull it apart. But what I have here is a piece of aluminum.
So now he's setting up C.
Aluminum is paramagnetic, so it is only weakly magnetized, so it's not really attracted to the magnets. Okay, so I also have two other pendulums. Okay, this one has slots in it, and this one, the slots go all the way to the bottom, so there's no connection along the bottom. Okay, and any of these I put in here will freely swing.
This is like a pendulum only, right? So that is an aluminum sheet, right? So which is actually, when taken to a certain angle with respect to the vertical and left free, it starts swinging.
Okay, so now let's see what happens when I try to swing this one through.
So can you guys tell me what exactly happened actually when it was swinging? It was swinging under the influence of whom?
Gravity, sir.
It was swinging under the influence of gravitational force. Now, this same energy from the gravitational force is actually taken into the magnetic field. As a result of which, see what is going to happen.
The magnetic field.
Did you observe?
Okay, notice how it breaks and stops. Now, if I did the one with the
So the one
slots,
which was swinging actually, when you took it into the presence of magnetic field, it came to an instantaneous rest. Right? That is why it is called as a breaking pendulum. So that was a complete sheet. Now he is going to take another sheet with some slots. Did you
we
observe
see
what
it
happened?
also
So the one with
breaks
the
and
slot
stops.
also
Not
came to rest.
quite as quickly.
Guys, did
And
you understand what happened? I'll show it again. See, when he released it, it came to rest.
We see
But
it
what is the
also
difference between the previous scenario and this one?
So it's having some
Came
partial.
to rest slowly.
So it came to rest more faster, right? The previous case, it was more sharp. Whereas now what is happening? It is trying to go to the other side, but it is being pulled back.
breaks and stops. Not quite as quickly.
Right? Am I right?
Yes,
Now
sir.
he has another aluminum
And
sheet
finally,
in his hand.
the ones
This one. Now, what do you think will happen when this is passed through the same magnetic field?
So it
It
goes to
will
the other
move
end.
further than the
Little
before
bit.
one.
It will move.
It will move further and
Then
comes to
come to
rest.
rest.
it will come to this. No. Check.
with the grooves so that there's no connection on the bottom swings freely. Okay.
What is happening?
What is happening is that
It's not stopping at all. Right. So, unlike the previous two ones, why is this not getting stopped is the question. Okay.
Connections
And the answer,
are below.
connections are?
Open. It's not closed.
That's right. Okay. Whereas the previous two cases, what happened? They came to instantaneous rest, right? So the answer to this question is because there is a production of circular currents in those metal sheets, and those circular currents are what are called as eddy current. Okay. Now we are going to see what is the logic involved behind this eddy current. Okay. So this was the sheet that they showed in the initial case. 1 minute, guys. Just give me a second. Now see. So this is the metal sheet they were trying to talk about. And the metal sheet is completely full. So there is a magnetic field, right? North pole and south pole. There is a magnetic field in this direction from the north pole towards the south pole. So remember, this is an aluminum sheet, which is paramagnetic in nature. Initially, when it is at position number 1, can you tell me, is there any flux linked to this sheet?
No, sir.
No, right? So as soon as it enters the magnetic field, what is happening to the flux? So initially the flux is 0. As it is entering the magnetic field, the flux will increase or decrease. The flux is going to increase. When the flux is increasing, what pole will get generated? The same pole as the one the particular metal sheet is facing. So the metal sheet is facing the north pole this side. So what will happen is there will be north pole which will get generated. Now observe guys. Now what I can say is there will be some small loops of current that is flowing in this circuit, and small loops of current is what we call it as eddy current. Okay. The small loops of current that we pass is what we call it as eddy current.
So can I give a statement, sir?
There is no statement involved. Like, you need to understand this. You read this, no? We have studied that electric currents induced in well-defined paths in conductors like circular loops. Even when bulk pieces of conductors are subjected to changing magnetic flux, induced currents are produced in them. So the induced currents which will get produced in the bulk sheet will be in small circular loops. And the small circular loops of current that is getting generated is due to what? Due to the change of magnetic flux is what we call it as eddy current. So generally eddy currents are nothing but they are some circular currents that are getting generated. So that's why some books refer to it as circular currents also. And some books refer to it as FOUCAULT, Foucault currents, because that is the name of the scientist who observed this. Okay. So that is happening with a completely closed sheet or a sheet with slots on it. But if you observe, it is not happening with the sheet which is having a comb-like structure because it is an open thing. So the eddy currents that we get generated cannot be in continuous loops, right? So that is the reason why there is no eddy current produced in this scenario.
Sir, why are these getting generated? So, like, what is the use of these currents, sir?
Use means they are getting generated. There is no use as such. They will only dissipate heat. See, sometimes what will happen is, if this sheet is there, no, if you try to pass the sheet through a very strong magnetic field, okay, let's say you have very strong magnetic field and aluminum sheet is passed through it, it will stop, no. Again, you take it outside, and if you touch and see, heat will get generated. Okay, so where is it getting? Where is the heat getting generated from? Generally, if you take a tire, okay, let's say there is a car tire and a car is moving on a road. When you apply some brake, what will happen? Due to friction, this will come to rest, right? When it is coming to rest, what will happen? You touch the tire and see, you can sense some amount of heat because there is a physical contact, and you know the reason that friction is the reason. You know the reason that friction is responsible for the heat to get generated. Whereas with respect to an aluminum sheet, when it is passed through something, heat is getting generated. So we need to understand what is the theory involved behind this heat to get generated, right? That heat is getting generated due to this. Okay. And due to this kind of a phenomenon that is observed, it is used in the magnetic braking systems. Because we understood that when a paramagnetic or a diamagnetic substance is passed into a magnetic field, it comes to rest. Means you can stop it without without having any physical contact. So you're using magnetism to create a braking system. Okay. So the applications that we have are these things. So the advantages is, see, first is you can use in the magnetic braking in trains. Okay. Second, you can use it in the concept of electromagnetic damping. So what do you mean by damping? Reducing the amplitude, right? So electromagnetic damping means, where does it happen? Certain galvanometers are there which have fixed core and a non-magnetic metallic material. Whenever this kind of a thing happens, okay, non-magnetic metallic materials means it is either paramagnetic or diamagnetic. So when they have a fixed core made of a non-magnetic metallic material, when the coil is oscillating in the presence of magnetic field, yes, there is a possibility of eddy current that will get generated. And due to this eddy current, what will happen is it will oppose the motion and bring the coil to rest quickly. Okay, so this is one of the applications. Third, it is used in induction furnace. So I told you, right, like how eddy currents can generate current, heat. Induction furnace can be used to produce high temperatures and can be utilized to prepare alloys by melting the constituent metals. So what will happen is they will take a high frequency alternating current and it will be passed through a coil which surrounds the metals to be melted. So what will happen when there is an alternating current? What do you mean by alternating current? It means the direction of flux is going to change with respect to time. So when there is a change in direction of flux going to take place with respect to time, there will be EMF getting induced in that metal, and due to that EMF, there will be circular currents, that is eddy currents getting generated in it, and that eddy currents will produce heat due to which the metals get melted. Okay, and the last one is electric power meters. So the one which we have at our home. If you look at the analog one, they will have a shiny metallic disc. Okay, so you can see a disc which is revolving. I'm not sure how many of you have observed it. It is there in analog meters. Whenever you want to check the units that you have consumed, then you can have a look at it. So electric power meters, what will happen? The shiny metallic disc in the electric power meter, the analog type, not the digital one, rotates due to the eddy currents. So electric currents are induced in the disc by magnetic field produced by sinusoidally varying currents in a coil. You can observe the rotating shining disc in the power meter of your house. If you still have an analog power meter, you can go and have a look at it. Have you ever observed, guys? There will be a number here, and above this number, there will be a metallic disc which will be revolving slowly to keep revolving. And that revolution is taking place because of the eddy currents. The reason why they told sinusoidally varying currents in the coil is because the power which we get at our home is alternating in nature. It's not a direct one. That is the connection to the next chapter. So if at all they ask you, like how they can ask questions is, why is the shiny metallic disc inside an electric power meter revolving? And the answer to that is very simple. It is because of the eddy current. So these kind of questions will be asked. Okay. So these are all the applications, and this is the whole concept of eddy currents. So I suggest you guys to read it once so that you will understand it better. Okay. And one last topic that is left out is AC generator. So this AC generator, we will discuss it in tomorrow's class and complete it. Okay. And from AC generator only, the next chapter gets linked to. The next chapter is slightly a tougher one. So I suggest you all to understand these concepts better, so that becomes easy. Okay, especially the concept of inductance and all, read and be ready, so that you will understand the derivations in the next chapter. Okay. Any other doubt, guys, from today's class?
No doubt, sir.
Okay, then we can wind up.